So let's take an example of that. Let's take this line, right? So this blue line that I have drawn over here, it is not a pipelining cut set. Why? Because the edge from 7 to 3 is going from bottom to top. The edge from 1 to 7 or 1 to 8 is coming from top to bottom, and the edge from 8 to 4 is again going from bottom to top. So once I have that kind of behavior, it means that it's not a feed forward cut set, but on the other hand, because of the presence of this register over here, I can do a retiming, meaning that I do a -1 on the edges going from top to bottom and a +1 on edges going from bottom to top. What would that look like? It would essentially say add one register here, delete this one, add one register here. Now what have I got? What does my resulting architecture look like? Once I have this, if I then go ahead and once again try to draw the dependencies, then what I have is, I have 5, 3, 1, 7 is now pretty much standing by itself. What about 6 and 8 are also standing by themselves, and 4. So now things are looking much more interesting. Effectively what it means is that at this point in time, with these two changes that I have made, 7, 6 and 8 all essentially have new setup where they don't have any direct dependency within this iteration, and their outputs are also not being used within the same iteration. In other words, they have complete mobility. They can be scheduled in any one of steps 0, 1 or 2. Okay, that's the problem. They can be scheduled in step 0, 1 or 2. I need to think one step further and see which one of them can go into 3. Okay, so even though I am sort of trying to do this systematically, the fact that there is a pipelining step over here is actually, or rather the fact that there is a spillover from one iteration to the next, I still need to take care of that a bit more carefully. Okay. If I try putting operation, so basically what I have is, this is how all the operations stand. If I leave the addition as it is, 4 and 2 over there, 3 and 1 over here, right, then I have satisfied all the requirements as far as addition is concerned. As far as 7, 6 and 8 are concerned, all three of them could go into operations into time steps 1 or 2 as well. I only need to make sure that if one of them can also be pushed into 3 without violating my constraint for the next iteration. Okay. What is that saying? It's basically saying that, for example, if I push 7 into step number 3, right, when will it complete? In step number 4, right? And the way that I can visualize that is to say, this blue 5, 3, 1 that I have drawn is the operations 5, 3 and 1 corresponding to the next iteration. Okay, and whatever I compute for 7 over here is then going to be used by 3 over here, right. So in principle, even if I move this down to this place and do it like this would be okay. And what about the other 2? I could easily just move this down, right. So what does my final schedule look like? It says operation 5 happens at time 0, its output is used by 3, that output is used by 1. Operation 6 starts here, operation 8 starts here, operation 7 starts here and goes over into the next iteration. Operations 4 and 2 are scheduled here. What do I have as a result? Number of multiplies, number of adds, I need 1, 1, 1, 1, 1, 1, 1, 1, and the max also is 1 each. So what happened over here? We basically started out with the original biquad filter structure that people are normally familiar with. We found that that has a critical path of 5 time units. I cannot directly schedule that within, and more importantly, even with 5 time units, I would end up requiring more than one adder and multiplier in order to get the behavior that I need. So then I said, okay, what kind of transformations can I make on this data flow graph that would allow me to bring the critical path down to 4 and also to break the dependencies in such a way that I can push the multiplications to different steps and the additions to different steps. Okay, and what we saw was, okay, let's look at the possible places where I can do pipelining and retiming, and we were able to identify fairly easily in this case 2 places where I could do the pipelining and the retiming such that the dependencies were broken. Okay. Now after that, of course, what we did was, it was still a little bit of looking at it and trial and error and sort of saying, okay, if I do it this way, then I can move this around, etc. There are procedures that can do this in a more systematic fashion, right? And that's what the entire study of scheduling techniques is about. Okay, so scheduling essentially talks about how do we systematically take a data flow graph that we have and get different kinds of hardware architectures, or given an architecture, get a different allocation of functions to of operations to hardware units, such that the hardware utilization is kept good, and at the same time maybe the total latency or the time required for finishing all the operations is kept to a minimum. Okay, you will notice that I am not talking about optimum, that is to say what is the best possible way of doing it. The reason is, it turns out that actually solving this in an optimal fashion is an NP complete problem, NP hard problem in general. Okay, that basically translates into saying that the only way pretty much of getting the best possible solution is to search through all possible combinations, which can be exponential in number. It can be a very large number in general, and there is no sort of systematic way by which we can do it in a limited set of steps, what's called the polynomial number of steps, in terms of the number of operations to be scheduled. There are no general solutions. There are, under some particular instances or particular special cases, there are solutions, but in general there are no solutions for this. Okay, so what we will do later is look at some kinds of scheduling approaches that are used in practice, just to understand how they could be used. But once again, remember, like I said, the goal of this course is not really that you invent new scheduling algorithms or that you evaluate them. It is more that you understand how the scheduling algorithms work, so that when we start looking at the hardware compilers, we understand what they are doing and are able to make better use of them.